Hello everyone, what's going on? Welcome back to Vedantu JEE English. My name is Pahul. If I'm audible and visible, please write yo in the chat box, you know drill. Yes, people. So today we are here to revise, discuss and solve questions of the chapter Aldehydes and Ketones. See, it's a very vast chapter and I'm sure you know that it's important for your examination because a multitude of questions come from this chapter. The approach that we will take today is a question-centric approach where we will see our previous year questions like we do and then we will try to revise the theory behind it. Alright? Because if we start doing aldehydes, ketones from the beginning, it will take a very long time. So the question-centric approach allows us to revise a lot of things in a short span of time. Therefore, we will use this particular approach. Alright? So this is the first question that we have in today's class. We'll be able to revise a lot of reactions today, by the way, so don't worry about it. So let's look at this one. What's going on in this? Obviously, when it came in the examination, it came with a bunch of options, but it's a pretty straightforward question, so you don't need the options. Also, one more thing, that in today's class, there will be some questions that feel like they are from the carboxylic acids chapter. See, the thing is that questions from aldehydes, ketones and carboxylic acids overlap with each other because from carboxylic acids you can make aldehydes or ketones, or if you oxidize aldehydes and ketones you can make carboxylic acids. So there's no particular need to actually distinguish between these two chapters when it comes to the questions. Let's solve this one. So what you have initially is, what is this, people? This is a can you see what type of a bond is this? Nitrogen bonded with a C double bond O. Can you see that this is just a cyclic amide? Yes. It's just a cyclic amide. So what will happen to an amide if you put some base in it and heat it up? What's going to happen? What will it do? OH negative is going to essentially attack here and the amide bond is going to open up. That's all that's going to happen. The amide bond will open up. So the first thing that you should form is something that looks like this. There will be the nitrogen over here which has the CH3 on top of it, and there is a negative charge on this particular nitrogen. Pretty simple. Now once you put the H positive, what's going to happen? This is just going to quench the negative charge. As simple as that. Yeah. So ultimately the product that you have to form is 1, 2, 3, 4 carbons. Yeah. On one side you have a double bond O, single bond OH. On the other side you have a nitrogen which has a hydrogen and another CH3. And this is literally one of the options. Yeah. So what did we realize over here? Base catalyzed opening of amides. What are amides? Amides are essentially a class of compounds that we call acid derivatives. Yeah. You remember what acid derivatives are? What are the different kinds of acid derivatives? You remember that? If you don't, let me revise it for you very quickly. This is your acid. Yes, if you remove the OH group and put a chlorine over there, this is known as an acyl chloride, or you can call it an acid chloride, right? Then if you bond it with another molecule of the same acid, yeah, acid can you see? You have removed a water molecule from between and there's a bonding that's happened between these two acids. This is known as the acid anhydride. Acid anhydride. Yes. Then what's next? The next compound is something that you've probably seen in your 9th, 10th class as well. This is known as the ester. After the esters, what do we have? The one that we just saw here. That's the amide. Cool. What's the Fun thing about all of these acid derivatives, if you hydrolyze these acid derivatives, you get the acid back again. So all you need to do to convert these into acid back again is just throw them in acidic water. Just put some H positive H2O, it will get converted back to the acid. There is one more acid derivative which is a little, no one thinks of it when you think of acid derivatives, but I'll tell you. Another acid derivative is RC triple bond N. You must be wondering, how is this an acid derivative? It's an acid derivative because when you hydrolyze this, it gets converted into the acid. Essentially, your OH groups get bonded to the carbon, nitrogen leaves away, and this is what gets formed. Alrighty, so people, keep that in your mind. Sivaraja, see, the initial product is cyclic, so the final product need not be cyclic. You are essentially opening the ring and then creating a straight chain structure. And the same thing could have been given the other way around as well. They might have given you the product, then given the same things, so you would have done the cyclization of the amide. Anyway, let's go to the next question now. Before we do that, let me remind all of you once again that if you want to enroll yourself in a test series that is of the all India level, JEE pattern helps you revise, helps you practice, helps you take mock tests, and then also helps you understand what's your rank compared to all the other students in the country. Vedantu has a free test series for you, the link of which is in the description box down below. Regular tests will happen, regular ranks will be provided to you. It's a very good opportunity for you to enroll into an all India level test series. It's all free, by the way, so you can just follow the link in the description box down below and that will take you to wherever you need. Also, we have daily practice problems available for free for you. Again, the links of all of these resources are in the description box down below. Once you open our website, it might ask you to log in with your email ID or your phone number. Just do that and then you will be able to access all of these things. Good. Alright, now let's go to this particular question. So you have a compound which is a diketone, yes? There are two ketones in the same structure. At the same time, you've been given OET negative. What is OET negative? This is what the structure of OET negative looks like. Ethyl alcohol's ion. What will it do now? There is a diketone and there is, what is this? This is just a strong base. So what is the typical reaction that happens when you have any carbonyl compound and a base? The only thing that is going to happen over here is your typical quintessential aldol condensation. There's going to be aldol condensation, as simple as that. Now, first of all, we will revise very quickly the mechanism of aldol condensation, see what the product looks like, what are the possibilities, and then we will come back to this question. Fine, let's do it. So what happens in aldol condensation is, let's say you take any aldehyde or ketone. Let's take this particular system just to start with. What is this? This is also known as acetaldehyde, or you can call it ethanol. First of all, you will react it with any strong base. What the strong base does is it abstracts the alpha hydrogen from this particular carbon. What is this? This is the alpha carbon. This is the functional group. This is the alpha carbon. So once the alpha proton is abstracted, it is pretty obvious that the carbon over here will be left with a negative charge. This particular species, my dear friends, it's known as the enolate ion. Yes, by the way, aldol condensation is the most important reaction from this entire chapter, so that's why I'm spending a little more time revising the mechanism for you as well. So this is known as the enolate ion. If you notice carefully, this negative charge is in conjugation with the oxygen. Can you see? This will move here, this will move here. So this is a resonance stabilized anion. Now what this anion does is it reacts with its own starting material. What was the starting material? Acetaldehyde. I'll make it like this. Yeah. So what happens here is that this species will react with its own self once again. And what will you form eventually? Now you have a new bond over here. Let's make that new bond with a green colored pen, just so that it's visible for you to see. Now this carbon is associated. It already has a hydrogen. Now the oxygen will turn into an O negative here, because these bonds would be polarized towards the oxygen. And there's already a CH3 on this particular carbon. Yes, once you quench this with water, this OH, this O negative will get converted into the OH group. Now what you can do is you can provide some heat to this particular compound that is formed. This is the first compound that is formed in the aldol condensation. If heat is given, then this can go a step further, where the OH group, this OH group and the proton that is present on the alpha carbon, the original alpha carbon, if a proton is present over here, you have two protons here of course. So one of these protons will get eliminated. You are essentially doing a dehydration. You are removing OH and H. Dehydration. Yes. So once the dehydration happens, what's the final product? The final product looks something like this. There will be a double bond formed at this particular position. Yeah. And then there is a CH3 over here. That's it. I didn't draw the hydrogen here because it's a bond line formula. You need not draw hydrogens again and again. So this is the final compound that you will form. What is the category of this compound? What is the kind of compound here? If your functional group is the carbonyl carbon, then this is your alpha, this is your beta. Such a compound is also known as an alpha beta unsaturated. In this case, you can call it an aldehyde, but in general, this is an alpha beta unsaturated carbonyl compound. Perfecto. So, whenever you see an aldol condensation happening, and if there is a heat, if there is an element of heat given in the reaction, then 99% of the times the product is going to be an alpha beta unsaturated product. Alpha beta unsaturated ketone is what you have to look for in the options, right? That's the first thing which will help you solve questions faster. Looking at the options, you'll realize, okay, there's only one alpha beta unsaturated carbonyl compound. So you'll just choose that and move ahead. But be careful. For this alpha beta unsaturated compound to get formed, you definitely need this particular proton over here. If by chance this carbon is substituted by more carbons, if there is no hydrogen here, then the elimination can't happen. So just make sure, if you're taking an answer just by looking at the options, seeing that, okay, there's only one alpha beta unsaturated compound over there, make sure you figure out the fact that there is a proton that you can use for elimination. That's it. Gym lovers, it's not my birthday. Cool people. Very nice. So over here, let's try to do the reaction. Now let's try to solve this particular question. How many carbons are there? 1, 2, 3, 4, 5, 6, 7, 8. Yes? 8 carbons. Fine. Now on these 8 carbons, there is a double bond O on this position and there is a double bond O on this particular position. Right? Now, my question to you is, see, whether you start the reaction from this side or from this side, it's the same, doesn't matter. My question is, will this particular reaction happen, or will you take the outer carbon and do this attack? Which attack will happen? Will the red attack happen or will the green attack happen? You tell me now. If the red attack happens, how many membered ring are you forming? 1, 2, 3, 4, 5. The red attack will give you a 5-membered ring. The green attack will give you a 1, 2, 3, 4, 5, 6, 7-membered ring. So the two choices that you have are one of a 5-membered ring formation, the other of a 7-membered ring formation. Which one do you choose now? Aishwarya and Pooja and Naveen and Sivaraja are telling me to make a 5-membered ring. Yeah, that's what you're telling me. So let me reveal the answer for you. That is absolutely correct. This is what's going to happen. This is not going to happen. Okay. 5 and 6 membered ring formation. All right. Formation is favored over 7-membered formation. Fine. Why does this happen? Can anyone guess? Why so? The reason is extremely simple. See, if two carbons are far apart, the probability of them swirling around and colliding with each other is very less. Isn't it? If two carbons are far apart from each other, then the probability of the entire structure getting twisted and then attacking like this it's difficult. But if the carbons are closer to each other, then their charges are also closer to each other. They can attract each other. That's the only reason. Okay. So generally speaking, 6-membered rings are the best because the ring that you form is also pretty stable. It can make the chair conformer of cyclohexane be super comfortable. 5-membered rings are also extremely possible. If there is a choice, let's say if there is a reaction where there's a choice of a 5-membered ring and a 6-membered ring, eventually we get both products in the laboratory. Alright, we get both products in the laboratory. 7-membered rings, the carbons are too far apart from each other to first of all attract each other and then react. So the probability of 7-membered ring formation is lesser. That's the only thing. Alright. Sivaraja, the sp3 carbons want to have a 109.5 degree angle in them. Can a ring ever be planar if the sp3 carbons want a bond angle that's not planar? Think about it. Yeah, cool. So 5-6-membered ring formation is favored over 7-membered ring, and therefore this is the reaction that's going to happen. So let's try to form the product now, and I'm sure after you see the product you will be able to guess the answer very easily. I mean, if you see the options, you'll be able to guess the answer very easily. Just let's quickly make the ring. So let's number this 1, 2, 3, 4, 5. Simply make a 5-membered ring over here. Done. Now let's number these as well. 1, 2, 3, 4 and 5. So on carbon 1, there is a C double bond O C already. Let's make that. Yeah, this is what this there on carbon number 1. On carbon number 5, there is another methyl group, and on carbon number 5, you will have your O negative, which will get converted to OH, which then will get eliminated from here and make a double bond here. Fine. So you have your alpha beta unsaturated ketone final product. Nice. Let's see the options now. Where is the remote control? There we go. Yeah, I'll remove everything so that you can see the options, but I'll keep the final answer over here. Can you see this guy? Perfect. So looking at the options now, there was a 7-membered ring option also. So maybe you could have made this mistake. Now you know that because of this distance, 7-membered ring approach is less probable. So now you won't make this error. Let me show you one more thing now. Let me show you one more thing, and this is going to be exciting or something that makes you happy, especially for those of you who've been attending my classes regularly. For my regular students, look at this question. Do you remember this? I have asked you guys this question sometime in the previous week. I've given this homework somewhere or the other, if you remember. Let's try to solve this question. This is a JEE Advanced 2005 question, by the way. Okay? Let's try to solve this question. In the first step, what you're doing is dehydration of alcohol. So what will happen here is that the oxygen will capture the proton and this will leave as OH2 because it's a good leaving group. So in the first step, we will have the formation of a carbocation that looks like this. Yes. Now this carbocation, there is a ring expansion possibility here, isn't it? Ring expansion can happen and then you will do the elimination. So let's do the ring expansion. I have taught you ring expansion last week, I remember. Let's do the ring expansion. So what we'll do, let's number this as carbon 1. Let's call this 2, 3, 4, 5 and 6. 2 and 6, the bond will break apart and 6 will now form a bond with carbon number 1. Essentially this. So there won't be any bond between 2 and 6 in the new ring, and carbon number 2 now will have the positive charge. Carbon number 1's positive charge is now satisfied with a bond. So let's make a 6-membered ring over here. Let's call this 1, 2, 3, 4, 5 and 6. Or I should do the numbering anti-clockwise like I've done in the previous structure, just for... yeah. Now it looks better. Alright. On carbon number 2 we have a methyl group, and on carbon number 2 we'll have the positive charge. Simple. Carbon number 1 is now bonded to carbon 6. Elimination. There's only one good possibility over here. Yeah. Elimination can either happen in this direction or in this direction. So let's make it in the ring. More substituted alkene has to be formed. So once the elimination happens, this is the product that you will get. Fine. This is the product. Now what you do with this is you have to do reductive ozonolysis. Reductive ozonolysis. What happens in reductive ozonolysis? You have ozone in the first step. In the second step, you have zinc. If in the second step you had H2O2, that will be your oxidative ozonolysis. In the second step, since you have zinc, this is called reductive ozonolysis. All you need to do in reductive ozonolysis is just break this particular bond. Just break this bond. And wherever you break it, put a double bond O. That's all. Wherever you've broken it, just put an oxygen over there. Let me make the final product for you. Double bond O here, double bond O here, khatam. That's all. Reductive ozonolysis. If this were oxidative ozonolysis, what you will do is, can you see a hydrogen over here on the carbonyl carbon? With oxidative ozonolysis, if there is a hydrogen on the carbonyl carbon, that gets oxidized to OH. So this would be the product if you had H2O2 in the second step. Since you have zinc in the second step, you won't do this oxidation over here. That's all you'll get. There is a hydrogen here. Chill. Fine. Now, let's simplify the structure. Let's write it in a straight fashion. How many carbons are there? I've got 1, 2, 3, 4, 5 and 6 carbons, and then there is a 7th one on the side. So let me make 7 carbons. Just a second. 7 carbons are there. On one side there is a ketone and on the other side there is an aldehyde. And now this particular structure is why you do aldol condensation again. This structure, you do aldol condensation, you get a 5-membered ring and not a 7-membered ring. Can you see? You get a 5-membered ring, not a 7-membered ring. One more thing it teaches you is that this is the carbon that goes and attacks over there, not this one. Yeah, this carbon is the one that attacks, not the other one. Very interesting. So the point that I'm trying to make over here is that if you solve old JEE advanced questions, you will learn a lot of things. In this question, you've learned about ring expansion, carbocation ring expansion. There are a couple of questions in JEE mains that came from this particular idea. Then you learnt about intramolecular aldol condensation, where instead of a 7-membered ring, you are forming a 5-membered ring. And when there are options, you are forming a certain product, not the other one. Yeah. So this teaches you what was required in the previous question. So a suggestion for all of you once again is, please solve these old JEE advanced questions as well, because they can directly be repeated in your JEE main examination. Fine? Alright. Aishwarya, if this is the case, then of course you will get a 5-membered ring. If this is the case, then you will get a 6-membered ring. Depends on how many carbons you have. If there's a choice between 5 and 7, choose 5. If there's a choice between 6 and 7, choose 6. But obviously most likely the choice is going to be between 5 and 7. Cool. Nice question, and we've revised a lot of things about aldol condensation just with one question. Nice. Now let's do this one. The major product P formed in the following sequence of reactions is... I'll show you the options in some time. Let's try to revise the reactions once again. You have an acid. First step, you put SOCl2. It's a chloride donor. SOCl2 helps you create acyl chlorides starting from acids. Okay. So, what's the starting material? Instead of benzene ring, I'll just write PH. Okay. How many carbons are there? 1, 2, 3, 4. 4 carbons. Now on the 4th carbon you have a double bond O, single bond OH. When you put SOCl2, the OH group of the acid is going to get replaced by a chlorine. As simple as that. First reaction is done. Now, the special thing about these chlorides is that these are extremely reactive, because the carbon-chlorine bond is not a particularly stable bond. Carbon-halogen bonds are not that great anyway. So this wants to break apart. What's going to help it break apart? The amine that you're using. You're reacting it with a 1 degree amine. So the lone pair of nitrogen is going to come and attack this carbon. Eventually the chlorine will leave away. Once the chlorine leaves away, what will you be left with? You essentially take away an HCl, Cl negative from here, H positive from here. So the second thing that you are forming in this particular reaction is another amide. Amide is formed like we had in the first question. So this is also done. Now the next step is addition of LiAlH4 onto the amide. LiAlH4 will add on to the amide. Now the interesting thing over here is that LiAlH4 is what? It is a hydride ion donor. Also, hydride ion donation means you are using it as a reducing agent. Fine. Acids and acid derivatives can be reduced by LiAlH4. Now my question to you is, this is an acid derivative. Using LiAlH4, what will this get converted into? After the combination of these two, there will be reduction. What should be the final product? Should it be an alcohol? Should it be an alkane? Or should it be an amine? What should be the product of reduction of amides via LiAlH4? Double Z is saying, I saw your reaction mechanism series, it was fabulous. I'm glad you liked it. RK is saying that it should get reduced into an amine. Omar is saying that the double bond gets reduced, right? Not in this particular, okay, I didn't make the double bond, I'm sorry. This is going to be here. That's not getting touched by anything. Sivaraja is saying it should form a secondary amine. Yes. Amine is what should get formed when you reduce an amide using LiAlH4. Let's look at the options now. These are the options that you have. Can you see which should be the answer? Over here you have an OH group and NHR. Over here you have some weird thing altogether. Over here you've reduced the double bond as well. This one, the double bond is intact, perfect. And the amide is reduced down to an amine. Done. Got it? Perfect. So just remember this idea that amides get reduced to amines using LiLH4. Simple as that. Cool. Now, there is one exceptional case where LiLH4 reduces the double bond as well. Only one exceptional case. Let me revise that for you. I think we revised it in the class in the previous week. Whenever we had the class, we revised it, right? If we didn't, let me do it for you once again. LiLH4, NaBH4, we were doing that in the alcohols class. So there is only one particular instance. This is known as cinnamaldehyde. In the previous question, there was one more single bond in the middle. So don't get confused between this structure and the one on the previous page. On the previous page, the double bond, there was another single bond and then the COOH. Over here, if you have this benzene and then next to it you have a double bond and just next to it you have a COOH, this is known as cinnamaldehyde. C double bond or single bond hydrogen, cinnamaldehyde. This, if reacted with LiLH4, LiLH4 over here can reduce the double bond. The only case in which LiLH4 reduces a double bond is that of cinnamaldehyde, no other case. So once this happens, there's a benzene ring. That's all. Your double bond is also reduced and your aldehyde is reduced to an alcohol. So we've done this in the previous week, but for those of you who forgot or maybe didn't attend the class previous week, just told this to you once again. Let's move on to the next question. This is a nice one. This is a good question. A solution of the product obtained by heating 1 mole of glycine with a mole of chlorine in the presence of red phosphorus generates a chiral carbon atom. Yo, someone knew what's up. So first of all, you need to know what's glycine. Yeah. Then the second statement says a molecule with 2 chiral carbons is always optically active. We know assertion reason questions become easy when one of them is wrong. Yeah, because the options will be like both correct, correct explanation, both correct, wrong explanation. One is correct, the other is incorrect. Yeah, that's the options that you'll have. So if you have one of the options that are incorrect, the answer becomes fairly simple. Most of the times you need to check only one of the statements. So we'll discuss the first statement in a while, but look at the second statement. A molecule with 2 chiral carbons is always optically active. That's a false statement. For instance, if we have a structure like this, both the carbons are chiral over here, this carbon and this carbon, both are chiral carbons, both have 4 different substituents on them. But because the overall molecule has symmetry, in the overall molecule there is a plane of symmetry in the middle. Therefore, the overall molecule becomes achiral. Yeah, these are also known as mesomeric compounds, or not mesomeric compounds, these are known as meso compounds. These are specifically known as meso compounds when there are 2 chiral carbons, but because of overall symmetry in the entire molecule, the molecule is achiral. What is chiral? Chiral means when your mirror image is non-superimposable onto the first image. Make its mirror image, flip it like this, you will get a superimposable mirror image. Very simple. Okay. So there we go. Someone, there's still a glitch, is it? Oh, I have no idea then why that's happening, because I restarted the entire system before this class. There is some sort of a system problem today. I don't know why that's there, Aishwarya. I'm sorry for that. I will tell the team to check for tomorrow's sessions. I hope it's not too bad. Maybe the internet connection has a problem. I don't know. Okay. Anyway, so there's a plane of symmetry. So second statement is definitely wrong. Let's look at the first statement now. The first statement says, if you have a mole of glycine, do you guys remember what's glycine? If you've studied biomolecules and if you remember at least the most basic amino acids, you would know what glycine is. Glycine is a naturally occurring amino acid. How do you make these naturally occurring amino acids? Let me teach you that. You make a V. On one side of the V, you make a double bond O, single bond OH, or you can simply write a COOH. Now on the other side, you make an NH2. Carboxylic acid, carbon, amine. These are also known as alpha amino acids, because on the alpha carbon, you have an amine on a carboxylic acid. Alpha amino acids. Now, on this particular carbon, you may have some functional group. Depends on what amino acid you are taking. So depending on whatever functional group you have over here, depending on whatever group you have over here, you have different names for different amino acids. The simplest amino acid known to man, the simplest alpha amino acid is where both these are hydrogens. Both the alpha substituents are hydrogens, and this particular structure is known as glycine. Cool. If one of these hydrogens is changed to a CH3, then what's the name? Can anyone tell me? If this is CH3, then this is known as alanine. All the naturally occurring amino acids have something here and a hydrogen here. Glycine is the only optically inactive amino acid. Okay? Glycine, if you see alanine, this is a chiral carbon, right? So all naturally occurring amino acids are chiral except for glycine, because glycine has just hydrogens here. So glycine is the only naturally occurring amino acid that is optically inactive. Great. Now, you react it with a mole of chlorine in the presence of red phosphorus. Can anyone tell me what is this reaction called? There is an acid-ish species, some acid, amino acid, and you reacted with Cl2 in the presence of red phosphorus. This is a reaction that comes every single year in JEE. Omar, very good job. The reaction is known as HVZ reaction. The full form of HVZ is Hell-Vollard-Zelinsky reaction. This reaction is just a simple alpha substitution reaction for carboxylic acids. So instead of one of the hydrogens, you will replace it with a chlorine. NH2. This is your COOH. And over here now you have a chlorine and the hydrogen was already there. So this particular carbon becomes chiral. And that's what the first statement is saying, that if you do that, it generates a chiral carbon. That's absolutely correct. So the first statement is correct, second is incorrect. Hell-Vollard-Zelinsky reaction. Now I would request all of you to take some time after the class is done and revise the HVZ reaction. From where can you revise it? you can use the Wikipedia page. Okay. You can simply go to google.com, type HVZ reaction. There'll be multiple web pages that open up. You can either open Wikipedia or there's another website called Master Organic Chemistry. Either of those web pages are good. Cool. Revise the reaction after the class is done. It's a very simple reaction mechanism. All right. Let's move on to the next question. Let's do this one. Two-step reaction, basically a roadmap question, sort of. Good one at that. What you've taken initially is a ketone. And onto a ketone, you've added a strong oxidizing agent. Can ketones be oxidized? How? And if you do oxidize the ketone, the hint is over here by the way, then on it you do some further reactions. So first step is to understand how to oxidize a ketone. And the thing is that JEE main over here should have given a little more information. Let me tell you what information should they give you. Let's make the enol forms that are possible for that ketone. This is one of the enol forms. Another enol form that is possible is this one. Ketonol tautomerism. So your ketone will have some enol form present in equilibrium with it. These are the two possibilities. Now, like you know, KMNO4 can break apart a double bond as well. KMNO4 can break apart a double bond and do pretty much the same reaction that you do in an oxidative ozonolysis. So you break apart either this bond or you break this bond. My question is, which one should I choose? Which enol form should I start my reaction with? And they haven't given any information. Let me tell you that when you do acid catalyzed enol formation, listen to me carefully. When you do acid catalyzed enol formation, the transition state that gets formed is an alkene like transition state. So in acid catalyzed enolization, more substituted alkene is better. In acidic environments, this is going to be present in a higher amount. In base catalyzed environments, this is going to be present. Because what happens in base catalyzed tautomerization is, the first thing you form, like you do in an aldol condensation, is you form an enolate ion. You form a negatively charged species. Now if you have to remove a proton from here versus a proton from here, obviously this is more acidic because it's less substituted. If you form a carbon ion over here, less substituted carbon ions are stabler than more substituted carbon ions. So if you had base catalyzed environments here, then this is where your enolate ion would get formed and this is where your double bond would be. So in an acidic environment, this is the enol form that's major. In basic environments, this is the enol form that you would have. Let's do one thing. Let's break both of them with KMNO4 one by one and see if the options can help us. Let's break the first one. Just a second. Yeah. Let's break this one. So now wherever you break the double bond, if there is a hydrogen present on the carbonyl carbon, you oxidize that as well. Let's do this one first. So R double bond O, I'll put an oxygen over here. Then you have this double bond O. And there's already an OH group. Perfect. This is what will get formed if you oxidize this with KMNO4. Since there is no more hydrogens on this carbonyl carbon, I don't need to do any further oxidation. Let's make the product from that. You haven't touched this side at all. Now, double bond O. Since there is a hydrogen here, this hydrogen will also get oxidized by KMnO4. It will turn into an OH group. And the other side, you have an OH group already, and this will also get converted into a double bond O. So from one structure, you are getting a ketone and an acid. From the other structure, you are getting both acids. Let's see the options. Which of these two structures is present in the options? Can you notice? Can anyone tell me? Let's call this structure X. Let's call this structure Y. I see this one. Yeah. This is your structure X, isn't it? This is your structure X. Great. The other one. Can you see this anywhere? How many carbons are there? R ke baad there is 1, 2, 3, 4, 5 carbons. On the fifth carbon there is a COOH. On the first carbon there is another COOH. What is this? 1, 2, 3, 4 and 5. But the good thing, okay, this one can't be the case because there's a CHO, but I need COOH. Look at this one. 1, 2, 3, 4, 5. So there is a COOH on one side and there is another COOH on the other side. So this one is your structure Y. You reject this. You obviously reject this as well. From these two, now you have to do the next step. So B and C both are still in the game. Now in the next step you have to see what you can do. So in the next step, what is this reaction called, people? This is a very standard reaction known as Wolff-Kishner reduction. Okay, this is a standard reaction called Wolff-Kishner reduction. So what Wolff-Kishner reduction does, okay, it simply converts aldehydes or ketones, essentially you can say carbonyl compounds, it converts them to alkane. That's the job of Wolff-Kishner reduction. It happens in a basic environment, and what it does is it simply reduces a carbonyl compound to an alkane. Over here I can see the Wolff-Kishner reduction happening properly. Over here, what is this going on? You're removing essentially two water molecules. Yeah. What you've done in the second step is you've removed two water molecules to combine this species. What is this called? Can anyone tell me the common name for this species? NH2NH2. You've combined this NH2NH2 in the place of the oxygens. Is it possible for this to happen? Maybe it can happen, yeah. But the thing is that you have KOH present. You have OH negative present. The OH negative will simply extract the hydrogens from the OH groups. Yeah, if these are the two acids, this hydrogen and this hydrogen will be taken away by the KOH. And then the O negative might attack somewhere else, and eventually, if you hydrolyze everything, if you're putting water, once again acids will get formed. Yeah, because whatever acid derivative you might have, if you hydrolyze it, it will get back to the acid once again. So if this is the product that you're forming in the first position, then the second case you won't have any changes. The same thing will get formed again because at the end you're putting water. Right? So this particular part is not particularly correct. This one is. This is a tricky question, honestly. They should have given some more information. They should have given the options a little more carefully, but they've made this into a very lengthy question. Yes, Samanyu and Sivaraja, this is known as hydrazine. Cool. Therefore, this is a lengthy question. I mean, it's not the most easy questions out there to attempt. So we revised a lot of ideas using one question yet again. How to oxidize ketones? What are the enol forms that get formed? In what conditions? What is Wolff-Kishner reduction? We've revised all of these ideas. Next question now. This is simpler. Okay. What's the major product formed in the following reaction? There is a substrate to begin with. In the substrate, you have an acid and at the same time you have an ester. Acid, ester, both at the same time, and you are using this peculiar reagent called LiBH4. See, we all know about NaBH4, we all know about LiAlH4. We've revised them extensively in the previous week in the alcohols revision class, or whatever revision class we had done. You revised this extensively. What is LiBH4? So what happens is, if in the laboratory you take NaBH4 and react it with some lithium, then what you form is LiBH4. And LiBH4 is slightly stronger a reducing agent compared to NaBH4. Compared to LiAlH4, it is not as strong. So if I compare these two to LiAlH4, then understood? This is the weakest, this is the strongest oxidizing agent. So in the laboratory, LiBH4 is synthesized when you selectively want to reduce esters. Used to reduce esters. Because I'm sure you remember from the previous week's class that NaBH4 does not react with esters. LiAlH4 reacts with esters and acids both. But then we have this LiBH4 in the middle, which does not react with acids but can still react with esters. So your acidic part will not get touched at all and the ester part will get reduced to the corresponding alcohol. So you have to choose an option wherein the acid is not reduced. This is rejected, this is rejected. This one, both are acids, doesn't make any sense. This one, there's an acid and an alcohol. Option D is the correct answer. Got it? So LiAlH4 reduces everything. NaBH4 does not reduce anything over here. LiBH4 reduces the ester but not the acid. So once again, after the class is done, just do a quick Google search for LiBH4, open its Wikipedia article, just read about it a little, see what are its applications. The main application of LiBH4 is of reducing esters selectively. Nice. Good question, right? Chalo, let's move on to the next one. If the font is too small, I'm sorry, I didn't have enough space to put things and the font size is weird, so let's just try to understand what's going on in this question. There are 4 compounds that are given to you and then there are 4 tests of these compounds. What are these tests? Let me write those down. First test says alkaline solution of copper sulfate and sodium citrate. So you have CuSO4 alkaline and you have sodium citrate. This is the first test. Second test says neutral FeCl3. The third test says alkaline chloroform solution. Alkaline chloroform solution. So essentially you have something like KOH plus CHCl3. And then finally you have potassium iodide Ki plus sodium hypochlorite. These are the 4 tests that are given, and corresponding you have to match them to the correct functional groups that they will recognize. What is the first reaction called? People, do you remember what test is this? This is a test for aldehydes. I'm sure you figured that out. Tollens test, Felling's test, Benedict test. Which one is this? There are three tests: Felling, Tollens, Benedict. Which one is this? This is the Benedict's test. Okay, this one is actually the Benedict's test. Can you tell me what's the difference between this and the Felling solution? What's the difference? The first solution is the same. It's called blue vitriol, CuSO4. Okay, fine. But the second solution is different. Over here it's sodium citrate. What's the other one? Solution B is sodium potassium tartrate. This one is sodium citrate. So this one is Benedict's test. Please keep that in your mind. And again, after the class, search on google.com Felling's test versus Benedict's test versus Tollens test. Check it out. Okay. So this is used to identify aldehydes. Even if you didn't know the name in the examination, it's fine. You should know that this is used to check for aldehydes. So this will mark with option number 3. Cool, this is done. Now let's look at neutral FeCl3 test. Neutral FeCl3 test is a quintessential test for phenols. Phenols, when they react with FeCl3, they give colored solution. It forms a very nice complex. Now the color of the solution depends on what's the substituent on the phenol. It may be blue, it may be green, it may be some other color. Depends on what the substituent on the phenol is. You do it in the laboratory, you'll know. Okay. So for example, if this was just phenol, it will give a different color. Phenol with substituted, something substituted on the phenol, this will give a different color. Essentially, FeCl3 test is used for phenols. Option 4 is done. Then we have KOH plus CHCl3. What does this do? We've revised this reaction also, if you remember. Haven't we? We've revised that. Where have we revised it? Let me remind you. If you have OH negative and you reacted with CHCl3, the first thing that you obtain is CCl negative. Yep. Now the K positive from here, or the Na positive if you had taken sodium hydroxide in the beginning, approaches the structure. It can stabilize the carbon ion, but there's another opportunity to form a very nice salt over here. So what will happen is chlorine leaves with sodium. Yes, chlorine also leaves from here, ultimately giving you a very interesting reactive intermediate known as dichlorocarbene. Do you remember this one? We've revised this in the phenols class when we were doing the very last reaction, Reamer-Tiemann reaction of phenols in the last week. This is the intermediate we had used. Remember? Reamer-Tiemann reaction, this will then react with your phenol and then it will give you a salicylaldehyde. Revise that again. But this dichlorobenzene can also react with 1 degree amines. This is what? This is a primary amine. How is it primary amine? You will say there are 2 carbons over here, sir. No. Look at the number of carbons on the nitrogen. Nitrogen is associated only with 1 carbon, so this is a primary amine. If nitrogen had 2 carbons, secondary amine. If nitrogen has 3 carbons, tertiary amine. Amines in alcohols are different. Don't confuse between their primary, secondary, tertiary. So this is a 1 degree amine. Okay. This is a 1 degree amine and this reacts with dichlorocarbenes. How does it react? I'll try to show it to you over here quickly. If you have your RNH2 and if you have that dichlorocarbene, you basically have to remove two HCl's from here. Basically, you remove two HCl's from here. It's a step-by-step mechanism. You can check out the mechanism after the class. So once this happens, you form this particular species, RNC. Isocyanides. Isocyanides. This has a very bad smell. It doesn't smell good. So whenever you do this reaction, if you take a base, chloroform, dichlorocarbene is formed, that reacts with 1 degree amines, a very foul smelling compound is formed, so you get a very bad smell. That confirms the presence of 1 degree amines. This test is also known as carbylamine test. Omar, yes, absolutely correct, bro. So this is your carbylamine test for primary amines. You get a foul smell when it reacts with dichlorocarbene. So dichlorocarbene in your entire syllabus has only two uses. One is the Reamer-Tiemann reaction. The other is carbylamine test. Perfect. So this is also done. And lastly, what remains over here? This one, they should have given KOH first of all. But theek hai, matlab this is also fine. If it had KOH over here for standard reaction, this is your halofoam test. This is your halofoam test, by the way. So halofoam test again, it's a standard test. You can go to wikipedia.com after the class, just look at it. It's a very easy mechanism. Revise it, okay? Multiple alpha substitutions happen first and then it gets converted into a carboxylic acid. Fine. So halofoam test, generally what you take is a base and a halogen. So you can do KOH and HI, KOH and I2, KOH or Cl2, NaOH and Cl2, something like that. But this is just a variation of that. Okay, iodoforms test variation. Now what gives a positive test with iodoform? I'll quickly revise the iodoform mechanism for you. Let me see if I have a blank page. Yes, I do. So if you have any particular species where there is a carbonyl compound next to a methyl group, over here whatever you have doesn't matter. Next to a methyl group, if you have a carbonyl compound, if you keep putting base into it, what will happen is one by one these protons will get removed, and in place of those protons you can put halogens. So the first thing that happens in the halofoam test is you form this particular species. All the alpha hydrogens of the methyl group are replaced by halogens. Then you take another molecule of base which attacks here and your CCl3 leaves. Eventually this is what happens. You have your OH here now and you have your C negative Cl3. At this particular position, in this particular step, very quick proton exchange happens because this is an acidic compound and C negative is not a very stable species. So very quick proton exchange happens here. You get an O negative, the hydrogen moves, and this is the final product of your halofoam reaction. This is a chloroform. If there was iodine over here, you call it iodoform. Presence of chloroform, presence of iodoform, it is smelly, it makes you faint. In the laboratory, if this is formed, it's very easy to recognize. And this is the side product, ion of the carboxylic acid. Got it? So you need to have a methyl aldehyde or a methyl ketone, or there's another group of compounds that give you the iodoform test, and that is if you have a 2-degree alcohol like this. If you have any alcohol which has a methyl group next to it, if you have a 2-degree alcohol like this, or if you have ethanol, This is what? Ethanol, CH3, CH2OH. So ethanol and any other 2-degree alcohol like this can also give you the iodoform test. So simply you oxidize this into the ketone or aldehyde first and then you do this reaction. So such alcohols can also give you iodoform test, not only aldehydes and ketones. So notice this alcohol. Yeah, this alcohol, if it gets oxidized over here, it becomes a methyl ketone and that will give you the positive iodoform test. Done. Now obviously this question, when it came in JEE, came with options, so it was much easier to just select an option, but now you know. Let's do this question now. Omar, if it is something that you can type here, then go ahead. Otherwise, you can get in touch with me on Telegram later. Let's do that, people. Manisha, what's up? So what we have over here is a, tell me the name of this compound. We've revised this in last week's class. Yeah, this is your salicylic acid. So salicylic acid, just a second. So this is salicylic acid. And on the right hand side, you have the esterification from the alcohol. On the left hand side, you have the esterification from the acidic part. And we've discussed this in the previous class. So what you have to do is, if you want to esterify the alcohol, you react it with an acid or a derivative. If you want to esterify the acid, you react it with an alcohol. So X is an acid or a derivative, Y is an alcohol. Let's see. X is an acid or a derivative. Yeah, okay. And Y is an alcohol. Okay, this is not an alcohol. Done. Option B is the correct answer. Pretty simple. Yeah. Okay, Omar Adnan is asking a question. 1-bromo, 2-phenyl, butane. There's a bromine here and there is a benzene ring here, is what I'm assuming. Is this the structure? And if you react it with OCH3 negative, what should be the product? And the reaction is in methanol. What do you think should be the product? Strong nucleophile. No heat is provided. The solvent is not water. So the probability of carbocation formation becomes very less. You should have a direct reaction over here and you will have an OCH3 associate on that position. So it's a substitution reaction, but the probability of a direct SN2 attack is much more compared to an SN1. Yeah. Omar Adnan, if they had heat over here, then yeah, elimination is a good product. But again, this is an ambiguous question. If they gave you the SN2 product and the E2 product both in the answer, then it's an ambiguous question, by the way. Yeah. Then in the laboratory, both things will happen, because this is a very simple 1-degree carbon. It is good for SN2 attack. Yeah. It is good for elimination also, because over here, if you form the double bond, it will be a nice resonated system. So in the laboratory, both will get formed. There is no one compound that should be major if heat is not given. Yeah, Omar, I know. This is a confusing point. The only argument that they use is that this is a better base compared to a nucleophile. That's the only argument that they give. So yeah, if now that you've seen this reaction, if JEE considers such cases to be elimination, now you know what to do if this question turns up in JEE again. If this turns up in JEE again, just simply do the elimination reaction, move ahead. But in the laboratory, both will compete equally with each other. Cool. Anyway, Manisha, thank you so much. Fine, let's move on to the next question. Can you tell me what's the first reaction that's given? What is this? NaHSO4. It's known as sodium bisulfite. So bisulfite, when it reacts with an aldehyde, this is known as a bisulfite test. Bisulfite test for aldehydes. Okay. So what happens in a bisulfite test? Let's do that over here. There's a double bond O. This NaHSO3, you can think of it as Na positive, HSO3 negative. What can happen is the negative charge can attack here, the oxygen captures a proton, okay, and then the oxygen captures a negative charge, and this negative charge can capture the HCl's proton. Cool, very simple. So what will get formed here? OH, there's a hydrogen here already, and there is an SO3H kind of thing that gets formed. Just an addition reaction. Now the thing is that this is a good leaving group. Since this is a huge structure, negative charge, if it comes here, is resonance stabilized on 3 oxygens, yeah? This is a good leaving group. So onto that good leaving group, if you put Cn negative, simple substitution reaction will happen. Cool, this leaves. So you now have a structure which looks like this. There's an OH group and there is a C triple bond N over here. I did not draw the hydrogen because I'm making a simple bond line formula. Now this compound is your compound A. Onto compound A, you either put LiLH4 to do a reduction reaction. LiLH4 will obviously react with the C triple bond and reduce it to, what will it reduce it to, tell me? And then you, on the other side you have HCl H2O and heat. What is this? Got the answer? So let's see the options. Sure, you'll be able to figure out what the answer is. Okay, perfect. My remote control is not working now. So keep this in your mind, okay? The structure. Keep in your mind. Let's see the options. This is the first structure that was formed. First two, these two get eliminated, of course. Now after that, what should be the answer? As we've understood just few questions back, that whenever you have a C triple bond N or an amide, that gets reduced to an amine. So the C triple bond will get reduced to an amine using the LiLH4. This is the first product. This C triple bond N gets reduced to an amine, so this is the second product. And option number C is simply the addition of H positive. Hydrolysis, acid catalyzed hydrolysis of C triple bond N gives you an acid. There we go. We're done. Cool. So in one case you get the amine, and on the other case you get the acid back again. Deepak, yes, you are correct. You will get the amide first, and then the amide will also get reduced further to the amine. Perfect. Nice question, right? So it again reminds you of the fact that whenever you have a nitrogen, it will get reduced to an amine, not an aldehyde, not an alcohol. Keep that in your mind. Chalo. Let's go to the next question. Simple question. You can actually solve this question without thinking about it. Without writing anything, you can solve this question. Let's think how to. Cyclohexylamine, when treated with nitrous acid, yields P. What is cyclohexylamine? Imagine there's a cyclohexane, there's a hexagon, on it there's an NH2. Now that NH2 is reacted with nitrous acid. What is nitrous acid? HNO2. I have revised diazonium cation for you in the previous week. Yes. So when you take that NH2 reacted with HNO2, you form N2 positive Cl negative type of a species. So now what you have is a cyclohexane with an N2 positive on top of it. You haven't reacted it with anything else. There is no 0 to 5 degrees Celsius given over here. And it is cyclohexane. It's not benzene. So the N2 positive is a good leaving group. It leaves, and what gets attached over there is an OH group that comes from water, because nitrous acid will be aqueous. So now starting from cyclohexylamine, you now have a cyclohexyl alcohol, cyclohexanol. Now you treat that with PCC, which means you oxidize the alcohol to the corresponding ketone. So you have a cyclohexyl ketone, cyclohexanone. That is treated with NaOH. So you take a ketone and you put a base into it, aldol condensation. What is the product? There is only one product that is an aldol product over here. There is only one alpha beta unsaturated compound. Yeah. If you had to form the alcohol, if you had to form the alcohol wala aldol product, then the alcohol should be on this carbon, no? Yeah. If you have to form the product of aldol without elimination, then this is what the product will be. This gets eliminated to form this. Since that is not one of the options, obviously, this is the correct answer. So whoever chose this option, good. Congratulations. Simple questions. Verbal question. You hardly spend like 20 seconds on such questions. Let's do this one. This is a verbal question, by the way. This is a JEE main question. Verbally, you can do this question as well. There is propanal and methanol. Dilute NaOH, aldol will happen, fine. Heat it, okay, you get that alpha beta unsaturated thing. Alpha beta unsaturated ketone. Onto the ketone, you add a CN negative. So what will happen? There is a ketone, C double bond O. On that C double bond O, now you put a CN, the O will turn into O negative. So you'll have a tetrahedral carbon with O negative, CN, whatever. You put water into it, the O negative will become OH, the CN will become COOH. Right? Now think. Whatever ketone we had, ketone is a planar structure. Let's say this is the C double bond O, okay? This is the C double bond O. CN negative will approach from the front and the back. This is the flat structure. Ketones are flat. So ketones can be attacked from the front and the back at the same time. So obviously a racemic mixture will get formed. We have our answer. What's the correct statement for product B? We know it's an acid and we also know it's racemic. You have your answer. It's a verbal question, but again, for those of you who are confused by that mumbo jumbo, I'll write it down for you. Don't worry. Let's do this question step by step. So first of all, you have propanal and you have methanol. 3 carbons, 1 carbon. Yes, don't make 2 carbons over here. That will be ethanol. So you have methanol, that is formaldehyde, and propanol. That is this. Cool. Now, obviously, there is no enolate formation possibility there. So what you do is you take this carbon, attack it here. Let's quickly do this. This is not changed. You get a new bond over here. On the new bond, you have a carbon that has an O negative. There are just 2 more hydrogens here, isn't it? Now this O negative, if you quench it, will turn into OH. If you eliminate it, you will form this. Why have I made OH? Sorry. Very sorry, people. This is a hydrogen. This is a hydrogen. Sorry for that silly mistake. Now, onto this, you add the Cn negative. So the carbon attacks this carbon. Oxygen pulls the electrons toward itself. And what's the structure we have? O negative. This double bond is not touched now. Hydrogen was already there. You have a C triple bond N. And now this is hydrolyzed. I'll make the hydrolyzed product here. Fine. What's the final product? Double bond O. There's a carbon. There is an OH group now. There is a hydrogen and there is a COOH. So this carbon that you get is a chiral carbon. There is a C double bond C. So this carbon that you get is a chiral carbon, and since the attack over here happened from both sides, front attack and back attack, you got both the enantiomers. Racemic mixture. C is the answer. Yeah. Sanjay, thank you so much, man. Badhiya? So racemic mixture and neutral. No, it's not a neutral species, it's an acidic species. It's not a neutral compound, it's an acidic compound. This gets cancelled. Optically active. See, racemic mixtures are not optically active. Do you understand why? Because racemic mixtures have the plus enantiomer and the minus enantiomer in the same amount. So overall the reaction mixture is inactive, optically inactive. Because half of the mixture is turning the light into the right hand side, half of the mixture is turning it into the left hand side. So obviously the overall mixture becomes optically inactive. That's why it's not an optically active compound. I mean, you get the point, right? You get a compound which has a chiral carbon, the enantiomer of which is optically active, but since you're getting a racemic mixture, the overall mixture is optically inactive. Got it? That's why racemic mixture. Alright. Vimala, the PDF of the last class, I am yet to share it. I will share it with the manager today and the manager will share it on the Telegram channel. Cool. Alright, this is done. Can you tell me the answer? Quickly, let me read the statements for you. There's a compound that's given. It has an alcohol and a ketone group. Can easily be reduced using zinc, mercury, HCl, and that gets converted into this particular species. What is this zinc, mercury and HCl? Zinc, mercury is also known as zinc amalgam. It's an alloy essentially. It's a solution of zinc into mercury. You take mercury, which is liquid, you put zinc, mix it, amalgam. So this type of a reaction is known as Clemmensen reduction. This is the acidic counterpart of Wolff-Kishner reduction. Wolff-Kishner reduction also reduces ketones to alkanes. Clemmensen reduction also reduces ketones to alkanes. The only difference is this is acidic in nature, that is basic in nature. Yeah, hydrazine, and then you had your KOH, OH negative over there. So this particular starting material has OH group. What happens when you do Clemmensen reduction with it is Yeah, you have your OH group over here. The HCl from Clemmensen reduction, H positive, the OH can approach this H positive. This can leave as a leaving group. This can become a carbocation, and then this carbocation will get attacked by the Cl negative of Clemmensen reduction, and this will get converted into a chlorinated compound. So if you do the Clemmensen reduction, the HCl will get used up by the OH group. So Clemmensen reduction will not happen. Something else is happening. Okay. What we call this type of a compound is an acid sensitive compound. Why acid sensitive? Because it's reacting with the acid. So acid sensitive compounds should not be used with Clemmensen reduction. What you can use over here is Wolff-Kishner reduction, because OH will not disturb OH. Even if it disturbs it, OH will get replaced by OH. Fine. So in this case, Wolff-Kishner reduction would be the choice. Clemmensen will not be the choice here. Got it? So assertion says this can be easily reduced using Clemmensen reduction. No. Second statement says Clemmensen reduction is used to reduce carbonyl group to CH2 group. Yeah, that is fine. But the first statement itself is incorrect. So A is incorrect, B is correct. I mean, assertion is incorrect, reason is correct. Got it? Perfect. One more corollary of this is, if you had this as your starting point, and if you wanted to do Wolff-Kishner reduction over here, this will not be possible, because now this chlorine will start reacting with this OH negative. OH negative will start substituting the chlorine. So this is now a base base sensitive starting point. Why am I making acids? This is a ketone. Yeah. So if you start with this particular compound, Cl negative can get displaced by the OH group. So in this case, Wolff-Kishner is not a good idea. This you can do Clemmensen reduction easily. Getting the idea? Chalo, that's also nice. Clemmensen, Wolff-Kishner, both are revised, both you know when to use them and when not to use them. I'm sure you will not do mistakes in the examination if you have a question from Wolff-Kishner or Clemmensen. Let's do this question now. Simple roadmap question. Very, very standard question. Shall we do it? So first of all, you have a methyl nitro on a benzene. You can call it para-nitrotoluene. And you are doing bromination onto the benzene. This is what? This is an electrophilic aromatic substitution reaction. We've discussed about electrophilic aromatic substitution in the previous week in both the classes. So what will happen here? Nitro group for electrophilic aromatic substitution is deactivating, since it is a -M group. It's a deactivating group and it is a meta-directing group. Right? Methyl on the other hand is a mildly activating orthopara-directing group because of its hyperconjugation. So methyl also activates this position, and the nitro, since this and this carbon are meta to the nitro, these carbons are where the reaction might happen. Since the overall benzene is deactivated, only single substitution will take place. Product A will look something like this. This is your CH3, this is your nitro, and you can put one bromine over here. Alright, fine. Just to remind you, if you take phenol in bromine water, phenol is highly activating, yes? So this gets converted into tribromophenol. OH, Br, and another bromine. Tribromophenol gets formed. So in order to do this reaction but not get multiple substitution, if you want a mono-substituted phenol, then you change the solvent here and use a non-polar solvent like carbon disulfide. Then you will get just a mono-substituted product. Okay, keep that in your mind. Since the nitro group is deactivating, there's only mono substitution. After the mono substitution, what you do is tin HCl, standard reduction reaction for the nitro group. Whenever tin is used, tin is generally a reducing agent. So tin will reduce nitro to an amine. Bromine, CH3, and the NO2 is now an NH2. Next step is diazotization. Yeah. 0 to 5 degrees Celsius NaNO2HCl. This will combine to form nitrous acid. So once again there is diazotization and the NH2 will now get converted to N2 positive Cl negative, diazonium cation. Benzene diazonium salt is formed. This is also a typical reaction of diazonium cations. H3PO2, whenever you use phosphorus species like H3PO2 or P4O10, these are called reducing agents or dehydrating agents. They will either dehydrate your mixture or they will reduce your mixture. Okay, so this is simply a reducing agent. Fine. H3PO2 itself gets converted to H3PO3. H3PO2 will get converted to H3PO3, so it will take the help of one of the oxygens from here. Overall, it's a reducing agent because on its own it is getting oxidized. So it will reduce whatever it reacts with. This will get reduced to, let's use the blue colored pen now. Bromine is not touched, neither is CH3. The diazonium cation simply gets reduced to a hydrogen here. If you want to form benzene starting from nitrobenzene, you first convert it into amine, make it into a diazonium cation, remove the diazonium cation using H3PO2, you will get a proton over there. Since this is a bond line formula, you don't need to make the proton. Nice. KMNO4, KOH, H3O positive. What should I do now? Alkaline KMNO4 and then you hydrolyze it. Can you guys tell me the last step? What should I do there? Deepak is saying I should do oxidation. Absolutely correct. What should I oxidize? Oxidation of the methyl group. Aishwarya, absolutely correct. So when you oxidize the methyl group, it will turn into a COO negative, and then when you put H3O positive over there, that will get converted into a COOH. Done. Tiger Tricks is asking, how do I increase my chemistry marks from 70 to 90 plus? Keep practicing previous year questions, my friend, as simple as that. If there is a topic that you want to improve, for physical and inorganic chemistry, you can read the NCERT, solve its questions. For organic chemistry, you can refer to my classes because organic chemistry in NCERT is not very detailed. Chalo ji. So this was your roadmap question, and now finally, this is a homework question for you. Do it yourself, please. Try it out. It's a very old JEE Advanced question, 2004. It's a simple question. There's only one possible answer to this question. Think about it. Spend some time with it if you want to. You will have fun, I'm sure. You can discuss this on the Telegram channel as well if you want. Nice. Sivaraja, I hope you're improving slow and steady. The only way to improve at this time, people, is to attempt more mock tests, analyze them properly, and keep solving questions. There's no other miracle way. The improvement now will only be gradual. So the first attempt, improve as much as you can, then keep improving for the second attempt as well, and then keep improving for JEE Advanced as well. Slow and steady improvements. Just be persistent with it. That's all. So people, the next class where you will see me is on Friday, and on Friday I will come in a marathon. Yeah, so there will be an entire marathon on the channel on Friday where multiple teachers will come. So you will see Shreyas sir, you will see Navamita ma'am, you will also see Namrata ma'am, you will also see me. Fine. So on Friday, when I will come live for you in the marathon is at 6 p.m. That's what's decided as of now. Cool. So on Friday, we will again discuss more questions of organic chemistry. Essentially, that's what you will do with me. All right. Someone new, I'll tell you the exact same thing, man. Yeah, I'll tell you pretty much the exact same thing. On Telegram, just remind me, I'll send you these images of an old NEET student who has, done very good analysis. Anand sir had posted those images in the founders Telegram channel some time back. I'll share it with you as well. Check it out. Deepak is saying, "Son, I feel without revising chemistry, my marks are decreasing." Then revise chemistry, bro. All right. Badhiya. Cool. People, if you have any questions, you can ask me right now. Otherwise, we'll end the session over here. Whoever is leaving right now, make sure you leave after hitting that thumbs up button. And I'm going to see you very soon on Friday. Cool. Badhiya. Chalo, that's it from my side, people. Thank you so much for joining in. I'm going to see you very soon. Until next time, good night. Take care.